Welcome to The Explainer. I am absolutely thrilled to have you with us today. We are about to go on a truly epic macro to micro journey across our very own spaceship Earth. We're not just going to look at our planet as some rock floating in space, but as a living, breathing, totally interconnected machine driven by some seriously cool physics and chemistry.
To get us started, I want you to just ponder this for a second. How does an invisible river of air in the sky create both the incredibly lush, biodiverse Amazon rainforest and the completely barren, dry sands of the Sahara Desert? I mean, it sounds like they should be created by totally different mechanisms, right? But as we're going to see, it is literally the exact same engine driving both of these extremes.
Okay, let's dive into this. Our itinerary for today. First, we'll hit the equator's engine of life. Then move on to Hadley cells and arid deserts. After that, we'll check out phytoplankton and marine ecosystems, explore forests, rivers, and global balance, and finally, wrap things up with monitoring Earth from space.
All right, Section 1, the equator's engine of life. Let's zoom right into the very middle of the map.
Right at the heart of this global engine is something called the ITCZ, or the Intertropical Convergence Zone. Now, because the Earth is heated unevenly by the sun, the equator gets incredibly hot. And this intense solar heating forces warm, moist air to expand, become less dense, and just rise straight up. At the exact same time, you have the northeasterly and southeasterly trade winds converging right at the thermal equator. They essentially act like a giant wedge, giving all that warm, humid air a massive nudge upward. This kicks off convection, creating what meteorologists actually call hot towers of cumulonimbus clouds that reach all the way up to the edge of our troposphere. And the result of all that rising, cooling air? Well, it's a staggering amount of rain. You see, because the capacity of air to hold water vapor drops as it cools down, all that vapor basically condenses out as really heavy rainfall. In places near the equator, like the Amazon River Basin, we're talking about up to 3,500 millimeters of rain annually. To put that into perspective, that's almost 140 inches. This constant cycle of rising humid air and torrential rain is exactly what fuels the extreme, vibrant biodiversity we see in tropical rainforests, giving millions of unique plant and animal species the perfect environment to thrive.
So what goes up must come down, right? Which brings us to Section 2, Hadley cells and arid deserts.
This brilliantly illustrates the complete atmospheric loop known as the Hadley cell. After those hot towers of air dump all their rain over the equator, the air doesn't just stop. It continues to rise to the upper troposphere and is pushed outward toward the poles. As it travels north and south, it cools down, and by the time it reaches roughly 30 degrees north and south latitude, this now cool, incredibly dry air begins to sink right back down toward the surface.
And this creates a really stark contrast on the Earth's surface. On one hand, you have the Amazon, which is fed by that ascending moist air and intense low pressure. But running on that exact same global engine, you have the world's subtropical deserts, like the Sahara, the Arabian, and the Atacama. These places lie right in the path of that descending, bone-dry air at 30 degrees latitude. As the air sinks, it actually warms up significantly and forms these persistent high-pressure belts. Because there's almost no water vapor left, there are pretty much no clouds to block the sun, which paves the way for scorching daytime temperatures and freezing nights. So the very same wind that breathes life into the rainforest effectively parches the world's greatest deserts. It creates extreme environments where only the most highly adapted, resilient flora and fauna stand a chance at surviving.
Let's shift our journey from the winds down to the water. Section 3, Phytoplankton and Marine Ecosystems.
You can think of the world's oceans as massive, heat-retaining solar panels for the planet. They absorb the vast majority of the sun's radiation, and living right there in these sunlit surface waters are phytoplankton. Now, these microscopic organisms might be tiny, but they are absolutely crucial. They form the base of the entire marine food chain and act as a massive carbon sink for the planet. Through photosynthesis, they use sunlight to combine carbon dioxide and water into sugars and oxygen. But here's the catch. They rely heavily on the upwelling of cold, nutrient-rich waters from the deep ocean to survive. When natural fluctuations happen, like an El Niño event, for example, which weakens the trade winds and warms the Pacific surface waters, that vital nutrient upwelling gets blocked. The phytoplankton literally starve, and those effects ripple drastically up the whole food chain, impacting everything from fish populations to seabirds and even higher-order marine mammals.
Okay, let's pull back and look at the big picture. Section 4, Forests, Rivers, Global Balance.
All of these systems build into Earth's ultimate long-term thermostat, which is known as the carbonate-silicate cycle. It essentially operates in 4 really fascinating steps. Step 1, carbon dioxide in the atmosphere dissolves in rainwater to form a weak carbonic acid, and this slowly weathers and dissolves silicate rocks on land. Step 2, rivers act as a delivery system, carrying these dissolved calcium ions all the way down to the oceans. Step 3, marine organisms, like those plankton we were just talking about, use these ions to build their calcium carbonate shells. And finally, Step 4, when those organisms die, they sink to the seafloor and eventually turn into solid limestone rock. Much later on, tectonic activity and volcanism will release that CO2 back into the atmosphere. So the crucial point here is that over hundreds of thousands of years, the simple act of rain falling on rocks and rivers flowing to the sea acts as a planetary thermostat, keeping Earth from either freezing over completely or turning into a boiling hothouse like Venus.
Which actually brings us to a really powerful quote from NASA. Carbon is both the foundation of all life on Earth and the source of the majority of energy consumed by human civilization. Now, Earth swings through natural climate variations, but the data clearly shows that human activity, primarily the burning of fossil fuels and mass deforestation, has added a lot of excess carbon into the fast carbon cycle. Our oceans have actually stepped up to the plate, absorbing up to 85% of this extra carbon over millennia. But, that comes at a cost. That excess CO2 reacts with ocean water to create carbonic acid, which reduces the available carbonate ions that marine life relies on. This process, known as ocean acidification, means that shell-building animals have to expend way more energy just to survive, resulting in thinner, more fragile shells, and that places a ton of stress on those marine ecosystems we just explored.
So, how do we keep an eye on all this? Section 5. Monitoring Earth from space.
To track this giant interconnected biological machine, international space agencies are teaming up to build some truly incredible technology. Right now, we're tracking 2 upcoming powerhouse satellite missions. First up is NISAR. This is a joint mission between NASA and the Indian Space Research Organization, slated for launch in July 2025. It uses a dual-frequency radar that can actually peer right through thick clouds and total darkness to detect movements on the Earth's surface as small as 1 centimeter. I mean, that is wild. It's going to monitor glaciers, earthquakes, and the carbon content of forests globally every 12 days. And right beside it, we have Trishna, a collaboration between ISRO and the French Space Agency. Trishna is going to use thermal infrared imaging with a stunning 57-meter resolution to give us the first-ever precise monitoring of plant water stress and evapotranspiration at a field scale. This is literally game-changing data for things like sustainable farming and global water management.
Collectively, you can think of these satellite constellations as Spaceship Earth's dashboard. Missions from NASA, ISRO, the European Space Agency, and JAXA in Japan are up there measuring absolutely everything, from soil moisture and ocean salinity to the exact thickness of floating ice and atmospheric greenhouse gases. They are completely shifting our scientific capabilities from just taking broad, fuzzy snapshots of the planet to gathering precise, high-frequency data that can actually help us resolve highly localized issues regarding our food and water security.
As we wrap up this explainer, I really want to leave you with a thought. We've seen how a single invisible river of air can build both dense rainforests and vast deserts, and how microscopic plankton and weathering rocks literally regulate the temperature of our entire globe. So the big question now is, how will monitoring our planet's vital signs from space dictate the survival of the incredible ecosystems we just explored? We have the dashboard, now it's totally up to us how we steer the ship. Thank you so much for joining me on this journey through Earth's climate engine. Keep questioning, keep learning, and I'll catch you in the next explainer.